I'd like to share a few thoughts with you about the implications for the discovery, should it occur, of extraterrestrial life for Jewish theology. What's theology? What is theology? It's a very, very loosely used term. But the Oxford English Dictionary says that theology is the study or science which treats of God. This is the Oxford English Dictionary, so it says his nature and attributes and his relations with man and the universe. Now, where would you go to find Jewish theology? Anybody? Where would you look? What? The Bible. Our distinguished guest on my left says the Bible. That's where I looked. Wisdom literature especially, and the later books of the Bible, being poetry, reflect theology, and the theology of educated Jews in one part of the biblical period. Now, it just so happens that one of the Psalms expresses a theology which deeply moves me, and which at the times at which it's recited probably moved you. And those of you who are active in Jewish religious life will recognize this passage. When I behold your heavens, the work of your fingers, the moon and the stars that you set in place, what is man? And that's Adam, which doesn't have any gender, that you have been mindful of him. Mortal man, that you have taken note of him, that you have made him little less than divine and adorned him with glory and majesty. You have made him master over your handiwork. That's from the Psalms. Now, what's the clue? Here we see a theology which says that God used his fingers to found, that's the term best translated, the heavens and the earth. And this passage announces that God and man stand in a relation to one another. And the essence of that relationship is that God is mindful of Adam, and indeed takes note of him. And the psalmist speaks to God calling him you. The pronoun, when it's used, is you, and the verb form is the second person singular, you, suggesting a reciprocal relationship that can be referenced using a personal pronoun. You caused the human to be little less than a god. You gave him the dominion over the work of your hands. So the relationship that's suggested by this particular poetic piece of theology is an intimate or personal one of you and thou. And who uses you and thou and I to describe the relationship between man and God? Anybody? Martin Buber. So here is a root of Buberian, if you will, theology, which must be one of the authentic Jewish theologies. Must be, I say, because it so wonderfully responds to the biblical psalmist, in the psalmist's expression of a relationship between God and man. And so the question I asked myself as I thought about this program is this theology, if you will, challenged by the discovery of extraterrestrial life? So I looked very, very carefully at the text, and I asked, does it say that the life which God brought into being on earth, because the word is haaretz, and that means the earth, is exclusive, that there's no other life anyplace in the shamayim, in the air, in the portion of the universe where the earth is not? And I found no such claim. You may say that the person or persons who wrote that passage thought that it was exclusive, but there's no direct evidence. I see our speaker is arriving, and so I'm about to yield this microphone, but not till I finish, which doesn't take long, by saying that indeed life above, outside, beyond the earth is suggested by certain passages in the Bible which are familiar to all of us. You remember what happened to Elijah? Remember? He was in danger, and a whirlwind came and snatched him up to heaven. So there is some area where there is life, because Elijah is thought never to have, quote, died, close the quote, that this Jewish theology contemplates exists beyond the earth. And that's not the only instance. We have angels, God's messengers. They're not on earth either. So the biblical theology that's expressed here wouldn't be offended by the notion that maybe there is some other extraterrestrial life. Now I'm going to ask this question, but I'm not going to try to answer it, because this is one I'm going to reserve for our speakers. So the question is, what do we mean by life when we talk about extraterrestrial life, or for that matter, life that's actually on the earth? And I have actually read a book and prepared a précis of it for you, but fortunately you don't have to listen to me much longer. But it gives me very, very great pleasure, if you're ready, Jennifer, for me to introduce you. To introduce Jennifer Wiseman, and at whose feet I have sat now on several occasions in her other capacity that I'll tell you about. But she is NASA's senior project scientist for the Hubble Space Telescope, and she is the director of the Dialogues on Science, Ethics, and Religion, known familiarly to those who love it as DOZER, a program of the American Association for the Advancement of Science. Dr. Wiseman is a graduate of the Massachusetts Institute of Technology, just down the river from where I went to school. They had to have real brains. They asked them really hard questions to which there was only one answer. We were able to fneffidate around when we took exams. And she earned her PhD from astronomy in astronomy from Harvard. And as far as I'm concerned, I hope you won't be offended if I say that makes you kosher. She previously headed the Exoplanet and Stellar Astrophysics Laboratory at NASA's Goddard Space Flight Center, and has served as an American Physical Society Congressional Science Fellow on Capitol Hill. Now, this is the one that really, I didn't know this, Jennifer, but this is really wonderful. She is the discoverer of the comet Wiseman-Skiff in 1987. So she is, in addition to being the head of such important programs, as an astronomical important person with an object named after her. And she is a former, in my book, anybody can get an astronomical object named after him or her, really has what it takes. And I know she has because I've heard her speak, as I said. She is the former president of the American Scientific Affiliation, an international network of Christians in the sciences. And so we are very grateful that Jennifer has agreed to come and talk to us. Welcome.
Extrasolar planets, this idea that there are planets outside of our own solar system, that was not even really discussed when I was in graduate school in the mid-90s because no one had really detected any or many. The objects that had been detected were kind of unusual and weird things. In fact, it was kind of an embarrassing topic to be involved with. People deridingly called it bean counting in my field because they felt that all it was just seeing if there was an exoplanet here and maybe one over there, but you couldn't do any scientific analysis of these objects. That has all changed drastically. Now, looking for and studying planets outside our solar system is one of the two highest priority science issues in astronomy and astrophysics in the nation today, as evaluated by the National Academies of Science. The other one being understanding dark energy and what is it that's causing the whole universe to accelerate in its expansion. These are the two major areas of focus in astronomy now. So the study of extrasolar planets and what's going on with life. So let me tell you just a little bit about where this fits in the whole picture here. We live in a bountiful universe. I use that word intentionally in my title because the universe is productive. It's producing things real time, even now, including new stars. And this is an example of how we know that. This is an image from the Hubble Space Telescope. It's an image of stars. This is a cluster of stars. It's a dense cluster called Omega Centauri. And I like this image because it is so beautiful, and it also gives you a sense of how stars differ from each other. So this particular image was made with the newest camera on the Hubble Space Telescope, the Wide Field Camera 3. And this new camera can see light in colors all the way from what we call near-infrared light, which is a little bit redder than what our eyes can see, all the way through the visible colors of the spectrum and into what we call ultraviolet light a little bit, so which our eyes also cannot naturally see. This camera can pick up that whole spectrum of light, and in this case, it's seeing stars that are radiating all the way from blue to red and a little bit in infrared and ultraviolet, and you can see that star differs from star here. You can also tell that there's a whole lot of stars here in this dense cluster. Our sun is a star in the Milky Way galaxy, but we're not situated, our sun is not situated in one of these dense clusters. If it did, we might have a very different night sky at night. What's also telling here is that you can differentiate star from star, and that's one of the advantages of having a telescope above the atmosphere, like the Hubble Space Telescope, which is in orbit, because you don't have the blurring effects of the atmosphere. So you can differentiate star from star. That not only makes a beautiful picture, but it helps us as scientists to understand stellar populations and how different groups of stars merge with other groups of stars and different ages of stars. If you can tease out star from star, you can do a lot of detailed studies about stars. So there's some beauty in there, and beauty of the heavens has inspired lots of deep thought, which I think we'll be hearing about a little bit later. But just to get you thinking, philosopher Immanuel Kant said that two things continue to fill his mind with ever-increasing awe and admiration, and this is written on his tombstone, I believe, translated roughly this way. Those two things that continued to fill his mind with ever-increasing awe and admiration were the starry heavens above him and the moral law within him. And so that's kind of interesting because I think today in societal conversations we're still having these two areas of thought as being something people are most interested in talking about. The starry heavens above, and today we might talk about it as science in general, what we're studying about the universe, what we're learning on the very large scale, what we're learning on the very small scale, and where do humans fit into that picture. And then the moral law within us, is there a moral law? Is there justice? What is justice? Who gets to decide what's right and wrong? How do we work together for a peaceful society? These kinds of things, and who gets to make those decisions and judgments, that's of constant conversation in society as well, and in religious communities as well. So those two realms that Kant was thinking about, we're still thinking about today. All right, so I'm getting to, this is a little backdrop so we can talk about where exoplanets and astrobiology fit in this larger realm of exploration. I've already mentioned that the universe is beautiful, but there's something more to this beauty. So here's the Orion region of the sky. For those of you who are stargazers, you'll recognize this region. This is an image taken with a telescope from the ground. It gets a wide field of view. You can see some of these famous stars known as the Belt and the Sword of Orion and Rigel. Anybody know what this big red star is called? Betelgeuse, right? So it's a well-known region of the sky, but if you look down around some of these central stars closely, even with binoculars, you'll see some fuzziness around them. That's what this little green box is pointing, just trying to guide your eye. The fuzziness around these stars, astronomers call anything fuzzy a nebula, all right? So there's nebulous regions around these stars, And if you zoom down in with a telescope that can get higher detail, higher spatial resolution, you start seeing something quite fantastic. So we're going to zoom in here with the Hubble telescope and see what we see down in here. And what we see is this, all right? So we've gone from this little fuzzy blob right here, which looks like a big bloated star. Zooming in, you actually see it's a quite spectacular, colorful nebula of gas. This screen doesn't do it full justice, but if you could see it on your computer screen, you would see this fantastic array of colors. And the colors come from the ionization that comes from new stars that have recently formed out of gas in this large, dark cloud, the Orion molecular gas cloud. Some stars have coalesced out of dense pockets of gas. They've turned on, because all a star is a collapsed ball of gas that's causing hydrogen in its core to fuse into helium, and that process releases light. The biggest stars release powerful enough light that the photons hit the surrounding gas, separate the electrons from the protons in the surrounding gas atoms briefly, and as they recombine, they emit colorful light that we see. So when astronomers see a colorful nebula, they say, aha! Recent star formation has gone on in this cloud. And if you look at this region with radio telescopes, as I have done, you see that there's a much larger cloud that lurks behind this little lit up region that's not lit up yet because no stars have formed fully in that larger cloud, but there are a lot of baby stars starting to heat up. We call them protostars, and you can see them with these other kinds of telescopes. So these are very active regions as well as beautiful regions. They fill up whole galaxies. So a galaxy like this is a collection of probably hundreds of billions of stars, also gas and dust between the stars. You can even see some background galaxies in this image behind if you look closely. All right. So we're seeing some of this with the Hubble telescope, which is orbiting the Earth even as we speak. And this is a very special year for Hubble because it's the 25th anniversary of Hubble's launch. So we're having a big international celebration all year going on. I hope you got to hear some, especially April, because it was actually launched on April 24th in 1990. And as some of you may recall, its first images were a little disappointing. Anybody remember that? Yes. We can laugh now. It was no laughing matter then, but thankfully, with some perseverance and support and innovation, the technicians and engineers found out a way they could correct Hubble's vision, and astronauts went up and put in corrective optics on Hubble and on all the subsequent instruments we put on Hubble. And since 1993, the telescope has been giving us perfect data, just wonderful. It's still at the peak of its capabilities. So this is a key part of the story, though, and that is that technology is opening up new realms of discovery, and then that is opening up new realms of philosophical and religious contemplation, all right, because we're discovering new things. Here's a graph. I know some of you can't see the details, but it's basically showing you how over the last 4 centuries, telescopes have gotten better and better. So the y-axis of this graph is showing you how telescopes have gotten more sensitive relative to what you could just see with your bare eye if you looked up into space. So from Galileo back here in the early 17th century, when he put telescope up, he monitored the motions of little lights around Jupiter that turned out to be moons. The eyepieces have gotten better, telescopes have gotten bigger. This is a logarithmic scale, so every tick mark here is 10 times more sensitive than the tick mark before it. At some point, photography was enmeshed into the idea of astronomy, so people could focus telescopes at space and collect light for much longer than you could just stare and see something through a telescope. So you could start to see very distant things that you otherwise would not see. And then electronic recording pushed us up another order of magnitude or so in the sensitivity of what you could see in space. So now you're getting to see galaxies, things like that. And finally, the idea of putting telescopes above the atmosphere came into play with the launch of the Hubble Space Telescope. That took us 2 orders of magnitude even more sensitive. We like to say Hubble changed the textbooks, and it really has, because what it revealed about the universe has really given us a new picture of where we are and what the universe is like. Then we've sent astronauts up to Hubble several times over the last few years to service it, and each time they've refreshed the telescope. The last time, we call Servicing Mission 4, it took us off the chart here. The new instruments are very sensitive. We have 2 cameras, 2 spectrographs in operation, and very good batteries, gyroscopes. The observatory is in really good shape right now, so that's really good news for astronomy. And this same kind of improvement has been happening in other types of science as well, and even with other types of telescopes as well, which we'll discuss in a minute. Hubble is unique in having astronauts that have gone up several times to do these refurbishments, and that's been an exciting and very important part of this mission. All right. So the new camera that these astronauts put in 2009 is giving us pictures like this, but it's helpful for us to see this in context. So this is a globular cluster of stars, but where is that? So this is a picture from the ground using a ground-based telescope. Gives you a broader field of view than Hubble can, toward the center of our galaxy. So you see a lot of stars and a lot of dust, but you also see some bright things. It turns out they're not single stars, they're whole clusters of stars. But this thing right here, let me tell you the punchline. You see this little thing right here? That is a globular cluster, and when you zoom into that thing, you see this, all right? That's the core of that globular cluster. So it's perspective that helps us see how things are distributed. And we're also learning through all of this that the universe is not stagnant, it's not just sitting there, it's absolutely active. So we have not only young stars forming, we have old stars that are dying, and as they die, they release their outer atmospheres. Here's the core of something called the Butterfly Nebula, which is an old star that's basically running out of hydrogen fuel in its core, and as it becomes unstable, it's releasing its outer atmosphere in this spectacular bipolar fashion. Larger stars that grow unstable will actually explode when they run out of inner fuel, and that explosion is called a supernova, and it disperses the guts of the star into interstellar space. All right? Now, it turns out that the fusion processes within stars create heavier and heavier elements. Original stars toward the beginning of the universe had hydrogen and a little helium and nothing else, really. And then over time, stars, through those fusion processes, have actually created heavier elements. The product of fusion can be carbon, oxygen, iron, and the explosion of a supernova itself creates heavier elements, all of this being dispersed into interstellar space. Why does this matter for our talk today? Well, it does because it turns out that generations of stars have come and cycled through our galaxy and other galaxies, and they produce these heavier elements, disperse them into interstellar space. The next generation of stars collapses out of interstellar gas, which is seeded with these heavier elements. So you now get stars forming that have some seeds of carbon and iron and oxygen, and you can actually get solid materials forming in disks around stars, and that's where we get planets. So stars are factories that create elements we need for life. We started seeing this for real in Hubble images back in the 90s, when here's another image of this Orion region with a different camera. But looking very closely, you can see these little baby stars that are trying to form, buried in these little pods of gas. But they have these disks of dust around them that are about the diameter of our own solar system. All right? So here we see some baby stars. Now they're going to have a hard time finishing forming because all of the bright radiation from these massive stars that have already formed are basically blowing away the material out of which these stars would have formed more completely. But they're trying to form. They're adolescent stars, and they're enshrouded in this dust. And a real hot topic now in astronomy is studying these disks around young stars, trying to understand how they form, what their structure is, and do they have planets embedded inside them? And how do planets form inside these dusty disks around stars? All right, finally, the universe is enormous in both space and time. I don't have time to do this topic justice, but here's our example galaxy again. But it turns out there are a whole lot of galaxies. There are hundreds of billions of galaxies. This is a deep field from Hubble where the telescope was pointed off in a direction of space that didn't have very many nearby stars, So it collected light for several days without being drowned out by something very bright, and instead revealed a lot of very faint things, many of them very distant in space. And it turns out these are all galaxies for the most part. These are collections of stars and gas. Here's a spiral here. Many of them have hundreds of billions of stars. And this is just one little soda straw area of the sky. If you imagine this extrapolated over the whole sky, you can get a visual image of how enormous the universe is. We think there are hundreds of billions of galaxies, each with hundreds of billions of stars, or many of them. That's hard to fathom, all right? And then some of these galaxies are closer than others, right? There's that third dimension. So astronomy gives us the chance to see back in time, because it has taken longer for the light to get to us from some of these galaxies than from others. And so we're seeing the light from some of them from an earlier stage in their existence than from other galaxies. And that gives us that time perspective. Here's an example of a reddened object buried deep in this deep field. It doesn't look like much. Even when you blow it up, it's just a blob, all right? But it's a very interesting blob. It's one of the most distant blobs we have ever seen. And it turns out this is a galaxy that's fragmentary. It's just starting to form. And the galaxy is shining to us from within the first few 100 million years of the existence of the universe. Now that sounds like a long time, but we think the universe, from various aspects of evidence, we think the universe began, our universe began with a very energetic burst of energy about 13.8 billion years ago. And it's really amazing that we can say to that precision, 13.8, give or take a little. And it turns out that we can now see light from proto-galaxies starting to form from within that first 0.8 of the 13.8 billion years. So we're able to see back pretty close to the beginning of the universe when stars were just starting to form, starting to collect into these little islands held together by gravity, what we call proto-galaxies, a few stars, a little gas, and then they started to merge and grow into bigger and bigger galaxies over time. So as our telescopes have gotten better and better, which is what this chart represents, better and better telescopes, better technology, seeing fainter things, we can see more distant galaxies because they're more faint. So these arrows represent seeing farther out into the universe. But of course, if you're seeing farther out into the universe, you're seeing farther back in time because it's taken longer for the light to get to us from these most distant galaxies or proto-galaxies. So from the 1990s, telescopes on the ground, through different improvements on Hubble, and even with the future James Webb Space Telescope, we're seeing farther and farther back in time, even to within the first few 100 million years of the universe. And we can compare what these galaxies are like back here in time with what the galaxies are like over here, closer to us in time. If this axis sort of represents time, toward the beginning of the universe to the present, we can compare, and what we find out is that the galaxies that are very distant are these little fragments made mostly of hydrogen and stars that contain hydrogen. And the galaxies closer to us in time and space, including our own Milky Way, are larger. They've gone through several mergers. They have had several generations of stars producing heavier elements. We see a lot of complicated elements and molecules in galaxies like our own, and that's taken some generations of stars to produce. So the universe has changed over time, and we can see that with telescopes. And it's provided the conditions that we need around stars in our own galaxy, in our own epoch of time, for the existence of planets and even life. So that is the point of all that, is telling you that the universe has changed over time to make some places hospitable for planets and life. All right, so that's very interesting. The universe has developed over time. It continues to evolve and change, providing conditions needed for life to thrive on at least one planet. All right, we found life so far on one planet. All right. There are 200 billion galaxies in the observable universe. All right? Now, if you think that there's something like 100 billion stars in every galaxy, more or less, That's the number of stars you come up with. All right? Now, what if just one star in a billion had a planet? All right? You'd still end up with a lot of planets. What if only one star in a trillion had a planet that had life on it? You'd still have quite a few, right? So the numbers are there. But how do we go about really looking? How do we fit in this amazing universe? Are we alone? And what can and can't science tell us right now about our place in the universe? All right. We are discovering that there are planets around other stars. That is one of the hot discoveries of the last couple of decades, and it is really exciting. This is an example. This is a real system detected in our own Milky Way galaxy. It's an artist's conception of a real discovery. So here would be a star and 6 close-in planets orbiting. If it were our own solar system, these would be planets orbiting within the orbit of Mercury. So this is a close-knit system. It's a real system, but it's detected indirectly. So artists have to come up with this nice picture of what it might look like. We detected it by looking at the star and seeing that it dimmed periodically when these planets orbited in front of that star, or what we call a transit, that when the planets orbit in front of the star and block out some of the starlight, what we see is that the total amount of starlight drops periodically. That's the technique that's been used by the Kepler telescope that NASA has had operating. It's not operating now, but it operated for several years, staring at stars in our galaxy, 100,000 stars, to see how they dimmed periodically due to planets orbiting around them. With that and techniques on the ground, the rate of discovery of exoplanets. So an exoplanet is exo, outside, a planet outside our solar system. That discovery rate has gone from basically 0 back in the late 1980s to onesies and twosies when techniques were first being developed to find these things, and then it skyrocketed. All right, so every year now, hundreds of these things are discovered. You have to do some verification. So there's now over 1,000 confirmed exoplanets and over 3,000 candidates that need some confirmation. So this is quite astounding, going from 0 to over 3,000 candidates. And this is in our own galaxy. So we're just detecting exoplanets basically in our own neighborhood in the universe. This could mean that there may be something like 20 billion planetary systems within our galaxy as we try to understand the statistics better of how many of these stars. There are estimates as high as 100, okay? It depends on how you interpret some of this data, but we're trying to understand how common it is for a star to have a planet. All right, so the Kepler mission and some missions on the ground have understood that some stars have planets, but how representative are they of all stars? That's the question right now. Let me tell you just a little bit of the techniques of how this is done. How do we detect exoplanets? It would be nice if we could just point a telescope up at a star and take a picture and say, oh, there's the planet, and there's the star, and there's several planets around it. That's nice. And look, that one looks like Earth. It's very hard to take an image of a planet outside of our solar system. Planets are very small. They don't shine their own visible light. They reflect light. They're typically, next to a big star, so they can get lost in the glare of that parent star. So astronomers have had to develop these clever indirect techniques to detect most of these exoplanets. One is to look for tugging motions on a star. So if there's a planet orbiting a star, they'll actually both be orbiting their combined center of mass. So what that means is that the planet appears to go around the star, but the star will wobble. All right. So if you can detect the wobble of the star, a star's motion, you can deduce what kind of planet or planets must be orbiting that star to cause that kind of gravitational tugging and wobbling. That's how many of the first exoplanets were detected. The second technique is to look for dimming when the planet transits in front of its parent star. That's the transit technique that I just mentioned. And then, of course, the third technique, which is what we would all love, is to take a picture of it. But it is difficult, not impossible always, but it is difficult because you have to suppress that bright starlight somehow to bring out the planet, which can be 1 billion times dimmer than the star. Astrometric wobbling, looking at a star's motion in the plane of the sky, that can be done. It's harder. Mostly we look at tugs going back and forth along our line of sight, that kind of wobbling. These guys Jeff Marcy and his colleague, whose name now escapes me, did most of the early detections of maybe the first few hundred exoplanets using telescopes on the ground, looking at wobbles, looking at the Doppler shifting of light of stars, and finding out what was causing that wobble. So they basically point the telescope, this is not to scale, of course, toward a star. The star is wobbling around the center of mass between itself and an unseen planet, and when the star is moving close, in the direction toward the telescope in that wobble, the light that we receive actually gets received at a bit of a compressed frequency, or it's blue shifted. When the star is moving slightly away from us in its wobble, the light we receive gets stretched out as it's moving while it's emitting light, so we get it at a reddened color, or it's red shifted. So by measuring the slight frequency shifts or color shifts in that starlight in this cycle caused by this unseen planet that's tugging on the star, we can tell that something's orbiting that star, and you can even tell to some extent how massive that planet must be, or within a range. Coronagraphs are what we use if we want to take an image of a planet, and again, you have to figure out how to block the starlight, and that's an ongoing process for astronomers, is trying to develop telescopes that can actually block out starlight adequately, as this gentleman's doing up in the upper left here, to have the happy planet appear, which is dimmer in the background. All right. Stars are 1 billion times brighter than their planets, so one way to try to see the problem is by thinking about a lighthouse being a star and a firefly being a planet. All right? I gave this talk in England once, a talk like this, and I used these slides, and they didn't know what a firefly was, so then I had to go through a whole entomology lesson. But anyway, the planet can get hidden in the glare like a firefly. But nevertheless, we have done some direct imaging. So this is a system called HR 8799. The star is being blocked out by the coronagraph, and out pops 3 planets orbiting this star. This was taken actually by a very good telescope on the ground, the Gemini Observatory. So we are doing some direct imaging. Usually it's a case like this where the planets are very distant from the parent star, so it makes it more possible to do this. All right. Transits, you simply look at the starlight itself, and it'll be bright, 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 and then it'll drop a little bit when the planet's going in front of it, and then it comes back to normal again. And that's very useful. You can learn a lot of things about that. And NASA, about planets this way, this is a telescope that NASA used for several years, which I mentioned before, the Kepler telescope, which did just that. It stared at 100,000 stars to look for transits. Let's see if this little animation will work. Okay, so here's a planet transiting in front of its parent star, and this is the total amount of light seen from the star. So it's up at a peak, and then it drops. The total amount of light from the star would drop as the planet goes in front of it, and then it goes back up again as the planet goes around to the side and behind. And by looking even at the slopes of these curves and things, astronomers can tell something about the nature of that planet. And sometimes you can even tell that there's more than one orbiting. So this is a technique that's being used heavily by astronomers. We want to know what fraction of stars in our galaxy harbor potentially habitable Earth-sized or Earth-like planets. All right, so that's kind of the question du jour. And we don't know exactly that number yet, and I don't have time to get into the statistics today, but it looks like on average every star has 1 planet. So some stars have more than 1 planet, some stars have no planets, but on average every star more or less has a planet. That's pretty amazing that we can say that now, right? Like 3 decades ago, we didn't know that. Now, that doesn't mean they're Earth-like planets. We're now trying to find out what fraction are Earth-like, what fraction would be in what we call the habitable zone of the star. We are doing things interesting with different kinds of telescopes to understand their characteristics. Some of them actually are orbiting double stars, all right? So that's an interesting case. With Hubble, we can actually look through the atmosphere of some of these exoplanets and find out what's in their atmosphere. These are examples of 3 spectra. So you take the light and spread it out into its constituent wavelengths of color, and different chemical elements or molecules will be absorbed by a transiting exoplanet, and you can tell what those elements and molecules are if you have a good spectrograph. So on Hubble there is one, and this is telling us the absorption of water vapor in 3 different exoplanets. So we're actually finding water vapor in some of these exoplanet regions. All right, so one of astronomy's highest goals, and I am finishing up now so we can hear from our theologian, yes? What if we're not the only forms out there? Well, one of astronomy's highest goals right now is to develop new telescopes and technology to directly detect and characterize Earth-like planets around sun-like stars within the next decade or 2, all right? So that's a big goal right now, and a lot of astronomers are feverishly trying to figure out what kind of telescopes we need that are better than the ones we have now on the ground and better than Hubble for this kind of thing, to search for habitable planets and to even search for the possibility of life. That's what NASA's doing, looking for primitive life or the signs of possible primitive life. On the other direction is the SETI program, the Search for Extraterrestrial Intelligence, which is not a NASA program, it's privately funded. And these folks are trying very hard to look for the possibility of intelligent civilizations intentionally trying to communicate with us, all right? So these are coming from 2 ends of the complexity of life spectrum, and yet SETI program is looking for intelligent life, NASA is looking for any signs of habitability or even simple life. If the goal is to find planets with evidence of life, most of the ones we've discovered so far are not really very good candidates because they're not in the right position relative to their parent star. They're either too close and too hot, or too far away and therefore too cold, or they have strange orbits that make them be hot and cold and hot and cold. And we do believe that liquid water is fundamental for life. At least it is for life on Earth. Now, of course, you can say, well, couldn't life somewhere else be totally different? Yes, all right. But we have to look for the kinds of life that we understand best, or else we're not going to recognize it. These are the kinds of planets as of September of last year that the Kepler telescope has determined. I know you can't all see this, but this is a histogram showing you different sizes of planets. So these are Earth-sized planets. These are super Earth-sized planets that are about 1.2 to 2 times the radius of Earth. These are Neptune-sized planets. These are Jupiter-sized planets. And these are super Jupiters, bigger than anything we have in our solar system. So it looks like, from our Kepler observations, that most planets in our galaxy that we've looked at are Neptune-sized, but there's quite a few that are Earth-sized or a little bit bigger than Earth-sized planets. So the fact that we can do a histogram of thousands of planets right now is pretty amazing. All right, I'm not going to go through all that, but we are looking for now to see how many, if any of them, are in the habitable zones of their parent stars. Some stars are smaller and cooler, so their habitable zones are closer in. Some are hotter, and so their habitable zones are farther out. So you have to factor in the nature of the star when you're trying to understand how many planets might be habitable. And again, Hubble is able to do not the detections, not the finding of these exoplanets, but Hubble does analysis of some of their atmospheres. As these planets transit in front of their parent star, the atmosphere of the planet can absorb some of the starlight on its way to the Hubble telescope, and then the Hubble telescope sees what's absorbed and finds out what's there. Hubble was the first telescope to use this technique to detect an atom in another planet's in an exoplanet atmosphere. It was neutral sodium, and then later on hydrogen, carbon, oxygen, and then, as I mentioned, water. All right. Eventually, we want to know if these planets are habitable. How are we going to know that? Well, we can't go there. They're too far away. So we have remote sensing. We will look, as our telescopes get better, for evidence for what we call biomarkers, elements and activity in the atmosphere that show us that signs of biological activity. So we'll look for evidence of oxygen. We'll look for evidence of liquid water. We'll look to see if the reflected light looks like it does when you look back at Earth and all the plant life is reflecting a reddened light. We'll look for methane. On planet Earth, a lot of methane is produced by living creatures, in particular cows, so we might find a bovine planet somewhere. So these are all things you would look for. Oxygen is produced here by plant life in abundance. That's what keeps our atmosphere full of oxygen. If we didn't have it constantly being rejuvenated, the oxygen would eventually oxidize out. So that's a sign of ongoing biological activity. But you have to rule out other explanations. So there's a whole field of astrobiology right now that's very active and growing, that NASA's supporting, trying to understand the conditions, the extremes of conditions that life exists on Earth, and what we will be looking for with telescopes when we look at other planets to see whether they are habitable for life. And we have to remember that we might be looking at an Earth-like planet at a very different age or stage than our current Earth. Our current Earth has not always looked the same. Some of our little most primitive life forms have been there since the Earth was only 1 billion years old. Our advanced life has only been here for a few 100 million years. So, chances are you look at an Earth-like planet someplace else, if it's developing the way Earth did, we might catch it in an earlier stage. So we have to realize that we might see something more similar to these methanogens and cyanobacteria that inhabited the Earth for very long periods of time on other planets. And what's on the planet affects its atmosphere. So here are concentrations of different gases in Earth's atmosphere at different epochs of time. So this is 4.5 billion years ago on the left side, and this is today on the right side. And so you see in the past there was much more carbon dioxide and very little oxygen. And then over time, a couple billion years ago, this changed. Methane came and went, oxygen grew, carbon dioxide fell. So if you look at an atmosphere at different stages of its development, it depends on what's been going on, what the life interacts with the atmosphere and changes the atmosphere. So what you're looking at is going to be different depending on the epoch of time. And of course, we might look at a planet that's much farther down the line than Earth is. What's that atmosphere going to look like? What would we look for? That's hard to predict. Philosophically, this is a nice bridge to our next speaker. Will finding exoplanets and extraterrestrial life affect our view of our own human significance? All right, that's a philosophical question. Are we less significant if life fills the universe, or does that make it more significant because the universe is full of life? Remember that being central may not necessarily have always been the sense of being significant. So even the Copernican revolution, that when we found out that Earth was not the center of the solar system, may not have been as profound as we look back on it today. In some sense, being in the center, at least in ancient times, and I'm a scientist, not a literature expert, but Dennis Danielson, who is a literature expert, wrote in the American Journal of Physics that actually in Copernican times being in the center of something was considered a demotion. Hell was in the middle of the Earth. So being in the middle, is that most significant? Is it not? These are philosophical questions. If life is rare, is that important or not? And I can go on and on, but I think I should turn over the mic to our next speaker. But let me just say that we've had different religious communities looking at this for time immemorial, even in the 15th and 16th centuries. And we finally, I think, come to the conclusion that everyone has a different response. The idea that there might be life everywhere gives people a range of responses ranging from wonder and awe to bewilderment to a sense of praise, to a sense of a loss of faith, to a sense of feeling insignificant, to a sense of feeling grateful and curious. So all those reactions are possible, and we'll hear what Rabbi Fred here has to say about the proper response. Thank you very much.